Hello, I welcome you all. If the supplied force F is equal to 150 newtons, determine the velocity of 50 kg block A when it has risen 3 meters starting from rest. This problem is coming from the Engineering Mechanics and Dynamics 14th edition by R.C. Hibbeler. So we have a system here. There's a force applied of 150 newtons, and we're being asked to determine the velocity of a 50 kg block when it has risen 3 meters starting from rest. So for this particular problem, if we wanted to know the acceleration at B, then we can use kinematics. But in this particular case, we are just being asked to find the velocity of A, which we can find directly by just finding the tension in the cables and later on use the equations of motion. So quickly, let's just do a section. We do a section there, we do a section there, we do a section there, like so. Once we do so, we are going to have this. So let's now transfer the force F. So we have force F here, right, which will be transferred there. Okay, and there it is going to be equal to there we go. We have that force there transferred the other side like so, and later on transferred there. Then we have it there, transferred there, and later on transferred down. Okay, and then there we go, we have it up like so. So if we have F here, if we have F there, we have F there, this is going to be F, therefore this one is 2F. So if this is F, this is F, this is going to be 2F. So if this is 2F, we'll have 2F there, this is going to be 4F, and so is this one. Alright, so we are going to have some weight there. We're going to have some weight, and this weight is just equal to W equal to mg, and this W is just equal to 50 times 9.81. Therefore our W will just be equal to 50 by 9.81. This gives us a 490.5 newtons. So with this information, it's up to us to choose which direction this is going to go. Okay, it doesn't matter as long as we are consistent with our units. So let's say this, we've chosen that this is going, let's say we say this is going, let's say this is going, so I'm going to do two cases. So the first case, case 1, I'll solve it differently. So I'll say case 1, we should be able to arrive at the same answer. So let's say our kinetic diagram, case 1, we have the system going down. So this is case 1. So let's say we have decided to say it's going down. Okay, the kinetic diagram is going down like this. Then this is our MA. Okay, on this particular case. So if it is like this, then we'll have the following equations from this. So we'll have W minus FA, I mean 4F, WA, this is just W, and then we have 4F equal to MA. Okay, W, we calculated this already, is 490.5, minus 4f. We know that our f is equal to 150 newtons, so this is just 150, and our mass, we know that is equal to 50 kg, so this is just going to be equal to 50 by AA. Okay, therefore our AA is just going to be equal to 490.5 minus 4 by 150 divided by 15. So we have a negative 2.19. Okay, mind you, we chose the kinetic diagram going down, therefore our acceleration just means it is going up. Okay, this is what it means. It means this is going up. All right, so once we have the acceleration which is going up, okay, we can now and we know to say this is constant. This is constant, so we can use these equations. We can say we want to find velocity, we have acceleration, and we have distance. We can use this equation: v squared is equal to v naught plus 2a s minus s naught, where v naught is just equal to 0 starting from rest. Our a is equal to 2.19 going up. Okay, going up, and then we have our s equal to 3, and we have our s naught equal to 0. Therefore our v squared is just going to be equal to 2 times 2.19 times 3. Therefore our v is just going to be equal to 2 by 2.19 times 3 square root of answer. We have a 3.62 meters per second going up. Okay, so this is case 1. We can solve this again. Let's say we assumed the kinetic diagram is going down, so we say case 2. This is for where we just have one system. We are not solving more than one we are not solving simultaneous equations. Let's say we have this system. Let's say we have this. We assume this is going up. Okay, it's going up. This is the same problem. Okay, and this is our MA. Everything else remains the same. We have F equal to 150. We have MA equal to 50 kg. Okay, so the equations now this time around, the equations of motions will have 4F minus WA is going to be equal to MAAA. Okay, and then this just becomes 4 by 150 minus 490 minus 490.5 equal to 50 times A. And then our A, if we calculated our A, our A is just going to be equal to 4 by 150 minus 490.5 divided by 50. This just gives us a positive value, which just simply means our acceleration is going up. This is positive, so it means it's going up. Okay, it's going up. Okay, in the other case it was negative. We had assumed the kinetic going down, so therefore, so in a case like this, well, we have found this. So, and this is also constant. This is also constant. So with this, we can also use again the same equation. V is equal to V naught squared plus 2a s minus s naught, where our V naught is coming from rest 0. Our a is just equal to 2.19. Our s is equal to 3, and our s naught is equal to 0. So we'll have v squared is just equal to 2 times 2.19 times 3. Therefore, our v is just going to be equal to 2 by 2.19 by 3. So the same answer, of course, which is just a 3.62 meters per second. Okay, so I just wanted to show for a problem like this, depending on which acceleration you use, the kinetic diagram you use, you just have to be consistent with the units for a problem like this. Okay, so there we go. So I hope this particular video was helpful, and if it was, give me a thumbs up. Like my video, continue subscribing and sharing my channel, and see you in my next screencast. If you wanted to compute the acceleration at B, then you can use kinematics to relate the positions so that you know the acceleration at B, or the velocity at B, or whatever at B. Okay, all right, bye bye, see you in my next screencast.